Hey everyone, so today we're going to be talking about the EMF, which is the electromotive force, and terminal voltage. So I'm just going to write out the equation that relates the two, and I think that'll help with understanding as we go throughout the video, and I'll reference it throughout. So we can say that this is the terminal voltage, V, EMF, obviously just the EMF, minus current times by internal resistance is the little r. So I'm going to first start out with explaining EMF, and then we'll move on to terminal voltage. So I want to get your thoughts on if this is a helpful analogy. So I'll explain it, and hopefully again that'll make sense. Say we've got a cart at the top of a hill. At the top of the hill, this cart has a potential energy of mgh. We'll say for our purposes today that potential energy is 120 kilojoules. When this cart moves down the hill and it reaches the bottom, all of its potential energy is then converted into kinetic energy. And although he had a potential of 120 kilojoules, when he gets to the bottom here, his total energy in kinetic energy might only be 119 kilojoules. And the reason for that is that some of that energy could have dissipated as heat. So we'll say that 1 kilojoule dissipated as heat, and you can feel that the wheels are getting hotter as he goes down the hill. In a similar way, if we've got a battery here, we've got our negative charge there, positive charge there, we've got this barrier, and then current is going to flow from this negative end to this positive end right there. And we define EMF. So we're going to say that EMF equals terminal voltage when I, or current, is equal to 0. So in a similar way that this card is starting out with 120 kilojoules, we might say that this battery is starting out with 12 volts. But because of internal resistance of the battery, what terminal voltage we'll get out might only be like 11.5 volts. Okay. So again, I want to hear if that was a helpful analogy, if that made sense. Really quick, I think what's important to understand. So if we're writing kind of a visual representation of something of a system. Sorry, I'm going to erase that. Okay, so this is little r, this is big R. So this is the EMF. So the EMF has got a battery, and then you've got the internal resistance here. This big R is the resistance of whatever it might be. This might be a light bulb. Anyway, so as I was saying before, you've got your EMF, again, maybe 12 volts. You've got a small internal resistance. So the amount of current that will be flowing, that will actually be usable in the system, might only be like 11.5 volts. And that's just because some of that energy dissipated as heat because of the internal resistance. That's why batteries heat up, is because they do have a small amount of internal resistance. And then that 11.5 volts can flow throughout the system. Now, I said before that electrons flow from the negative end to the positive end, so you would think the current would be going that way. The convention in physics, just because of how it was discovered and some other things I won't go into, it's convention for the current to flow from the positive end to the negative end. So we're going to say the current is flowing this way. So again, so if we're talking about voltage sources, so voltage sources have always two components to them. They have a source of electrical energy. So the source of electrical energy is this potential difference from the negative to the positive charge. And because there is a barrier, I'll draw this really quick. So we're going to say that this is, sorry about that. This is the cathode. And this is the anode. This is the negative end. Anode. Usually batteries have some kind of like sulfuric acid in there. So you've got a barrier here, so these negative charges can't flow directly into here. They have to flow through here, like a copper wire or something, and that's what creates a current and what generates, and that's what generates energy. So you've got to have a source of electrical energy, and then two is there's going to be an internal resistance. Okay, so that's in all voltage sources except for special cases like superconductors that we won't get into. But so really quick, so this, we're going to say that this is a car battery. So we've got a car battery. We'll say this thing's 12 volts. And then we will say this is like a motorbike. This has got 12 volts. So it's going to be important to know that in bigger car batteries, or in bigger batteries in general, even if they have the same amount of voltage, this car battery is going to have a lower, it's going to have a lower internal resistance. And if it has a lower internal resistance, remember that our equation looks like this: EMF minus IR. So if it has a lower internal resistance, it's going to have a higher terminal voltage. But you can see how if you were to mess with this, so if you were to increase the current, you're going to decrease terminal voltage. And if you increase resistance, sorry, I think I said that backwards. So if you increase current, you're going to decrease voltage because there's a negative sign here. If you increase internal resistance, you're going to decrease voltage. So that's my video on EMF and terminal voltage. So you can again just think of terminal voltage as kind of the potential energy, or all the energy in the system. But part of all that energy is going to be converted into heat, which is why a battery heats up. And the actual voltage that you get into the system is going to be known as its terminal voltage. And you can see that the equation's right there. So again, I'll just show that one last time. And thanks, guys. That's my video.